All right, we'll continue. At the end of the last segment, what we saw was that we have essentially got away from the notion of the body having to be included when we describe motion, right? We have a way of going from our reference configuration, say omega naught, with the reference position of a material point capital X, to the current configuration of the body omega sub t with the current position of a point x sub t, right? And this is all in three-dimensional space. Okay, and in particular, the way we were writing this map, we decided to use a new symbol f sub t of omega naught, right? And what this also does for us is maps individual points, right? It maps that reference position x via f sub t of x to little x sub t. Okay, you observe that we've managed to do this now without describing the body at all, right? We're just talking about how one configuration maps to another. In particular, we're talking here about how the reference configuration omega naught maps to a current configuration omega t. Okay, so let's just recall some notation, right? Omega naught is the reference configuration omega sub t is the current configuration x is the reference position x sub t is the current position. I should also mention that especially in the case of solid bodies and in the case of fluid bodies also, the reference configuration is often thought of conveniently to be either an undeformed configuration or a stress-free configuration. Right? So if this is the reference configuration, it may be undeformed or stress-free, and therefore the current configuration is often thought of as a deformed configuration or one in which there is stress. Okay, so if this is the reference configuration, in the context of solid mechanics, we may say that that's the current configuration, and furthermore that this current configuration is deformed, right? So this, all right, there we go, it's deformed. Okay, so let me just state that. Let me just state here, okay, that this is often called the deformed configuration, and in that context the reference configuration is often called the undeformed configuration. Okay, so we have here x sub t is got through this mapping of capital X. Okay, now the subscript t here represents time. It's often common and it's actually quite convenient if we just recognize that, well, in exactly the same way as this mapping is parameterized by reference position, we can also include the time t as a further parameterization of this mapping. Okay? So the other way in which this is often done is to simply write x as being the current position obtained through a mapping of the reference position x at time t. Okay? And in that context, if we agree with this representation, then when we come back to this one, we just think of it as being at some fixed time t. Okay? The one on the left. Okay? All right. All right, so let me draw things here yet again. We have our reference configuration, the current configuration, right? And actually, let me follow our new notation and not use omega sub t there, okay? Now we have the idea that this mapping is phi of x comma t, which takes the reference position of a point to its current position little x at time t. Because of this sort of idea that phi takes a point which had position x in the reference configuration, capital X in the reference configuration, to position little x in the current configuration, phi is also often called a point-to-point map. Okay? Furthermore, for our purposes, we will simply now refer to phi as the motion. Okay? So phi, a point-to-point map, is henceforth to be called the motion. Okay? And let me write this. It may seem like we are belaboring this point right now, but it's actually useful for later on if we describe this in as many ways as possible. Okay? X equals phi of x comma t is our point-to-point map, right? It maps reference position capital X to current position little x at time t. Okay? All right. Let's introduce some notation for all of this. Observe, of course, that capital X and little x are vectors, right? So now we can write them out in terms of their components relative to our basis, right? Our basis here is E1, E2, E3. Okay? So X is a position vector. In particular, it is the reference position vector, right? So what this implies is that X is X sub I E sub I. Okay? Sum implied over capital I. X sub capital I represent the components of our reference position relative to our basis. Okay? It is going to be notation that we will follow that capital X will have uppercase indices for its components. Okay? And this simply is going to be a way in which we are going to remind ourselves that capital X sort of lives in the reference configuration of the body. Okay? So we're going to follow this notation that vectors and tensors in the reference configuration will have upper case indices. Okay? So uppercase indices for vectors and later on tensors when we start introducing them again in omega naught. Okay? And our first example was right here. X equals X sub I E sub I. Okay, it's just a way for us to remind ourselves as we get deeper and deeper into our coordinate notation that a particular vector or tensor lives on the reference configuration. All right? Now, what about little x? It's also a position vector, right? It is the current position vector. Okay? It too can be written in terms of its components. Because we think of little x as being the current position and something that lives on the current configuration, we're going to use lowercase indices for it. Likewise, any other vector or tensor that lives properly in the current configuration is going to have lowercase indices for its components. Notation, that's all. Okay? So we will have lower case indices for vectors and tensors on omega. Omega in general is our representation of a current configuration at a particular time, right? So omega, remember, is phi, omega sub t would be phi sub t of omega naught. Okay, that subscript t just reminds us that it is at a particular time t. Okay, in general we will refer to the whole set of current configurations as omega, right? And the sub t being for a particular time. Okay, so observe however that x is equal to phi of capital X comma t. It follows that our point-to-point map phi is itself a vector map, right? So we see that xi ei is equal to phi sub I parameterized by reference position and time E sub I. Okay? Right? This is all just notation to help us with things in future. All right. What I'm going to do now is write out an example, a very simple example of motion as expressed by phi. Okay? Let's do the following. I'm going to do it in 2D simply because it's easy to describe. Well, it will be 3D, but the most interesting aspects of the motion that we are going to look at will happen in 2D. Okay, so let me see, how am I going to do this? All right, let me write our basis vectors as E1, E2, E3. Okay, I am going to draw out the reference configuration of the body here. Right, it is in 3 dimensions. Okay, that edge is aligned with E1, and so the horizontal edge is aligned with E1, the vertical edge is aligned with E2. That edge is the one that is aligned with E3. Okay, so this is omega naught, and what I want is that the body should be deformed into something that I will take great pains to draw. Okay, what I'm trying to represent here is that the body is being sheared in that E1, E2 plane. Okay, so this is omega. All right, and I have here the motion phi of x comma t. All I'm going to do here is give us a very specific example of how we may represent motions using phi. Okay, so what we want to do here then is write x sub I, which is phi sub I function of x comma t. All right. We can do this now by writing them as follows, right? So we want to specify the x sub i's, right? We can do that by saying that x1 equals, let me see, how do we go about this? Right. We want to make x1 be, right. We want to make it the tangent of some angle gamma, okay, sub t. Gamma is going to depend upon time, all right, multiplied by x2, all right. And the idea here is that gamma is that angle, gamma function of time. Okay? Clearly, for a given value of gamma, tan gamma is going to give us the extent by which a point here, for instance, a point there has been deformed to go there. And the amount of deformation along the E1 direction is that arrow, which is given by tan gamma function of time multiplied by x2. All right? The other positions, the other coordinate positions, if you like, remain the same, right? They remain unchanged. Okay? All right? The x2 position stays the same, likewise the x3 position. Okay? All right? So, if we now put all of this together, I'll do it right here so that we can see what we're doing. What we have is that x equals phi of x comma t, which is now written as tan gamma function of t times x2 E1 plus x2 E2 plus x3 E3. Okay? This then is our first and admittedly very simple example of a motion, right? It is what we may call simple shear. Okay? All right, we'll stop here with this segment.